We're going to do a little bit of quantifying of ionic and covalent bonds in this video. We have generally talked about ionic bonds being a transfer of electrons, covalent bonds being sharing, but there are ranges and degrees of sharing and degrees of transfer. So we're going to break them down into some more specific categories, and we're going to talk about how we put something in a category. And then what do we do with that information? So to quantify an ionic or covalent bond, calculate the difference in the electronegativity. And I've got absolute value around here. You just want the difference. The positive or negative doesn't mean anything. All we want to know is how much are these electrons shared or not shared. So since electronegativity is the ability of an atom to pull electrons toward itself in a bond, a small difference in electronegativity means they're both kind of pulling equally. You can think about it like a tug of war. Those are pretty well shared. If there's a big difference in electronegativity, right, one atom is a lot stronger in this tug of war, that means not very shared. So that bond is more ionic. It may not be far enough for us to call it ionic. And we have some cutoffs that tell us, like, is this an ionic bond or a covalent bond? Now, within the covalent bonds, we also have another category that I have listed here. So we have a non-polar covalent bond. So this is for something where the electronegativity difference is between 0 and zero point 0.4. So electronegativity difference of 0, right, that's going to happen in things like H2, BR2, all of our Brinkelhoffs, where the electronegativity of each atom is exactly the same. They are perfectly shared. And even if like one is pulling just a little bit more, we would call that a non-polar covalent bond. Now, the next range from 0.4 to about 2, we would call that a polar covalent bond. And so, right, if you think for polar, non-polar, think about it like polarized, poles of a magnet. Polar covalent means they are shared, but the electrons are definitely pulled more in one direction than they are in the other. And then above a difference of about 2, we would call this an ionic bond. Now, you do not need to know these cutoffs. I just want you to be able to picture in your head if someone talks about a non-polar covalent bond, what that means in terms of like a small difference in electronegativity versus a polar covalent bond, what the electronegativity difference might be like for that bond. So we've got to give a couple of examples, right? A carbon-hydrogen bond. Now, this has an electronegativity difference of exactly 0.4. And there's no less than or equal sign in this range. So my goal will be to never ask you explicitly about a carbon-hydrogen bond because in reality, what we say about this bond depends on the context. So like, what would I say? I would say it's like kind of slightly polar covalent. Like it's on the borderline between nonpolar and polar. If you ask an organic chemist, they would just be like, this is nonpolar. Why are you wasting my time by asking me this question? So right, even when chemists talk about these things, there will be differences, but this is just to kind of give you a frame to know that there are ranges and that we will talk about two different types of covalent bonds that just refers to the degree of sharing that occurs for the electrons. We represent this unequal sharing in a couple of ways. So I've got HF, so hydrofluoric acid, as an example for us to look at. I almost have a Lewis structure here. I don't have lone pairs on my fluorines, but right, hydrogen connected to fluorine is the basic structure of my molecule. Look at the electronegativities. Fluorine is more electronegative. This is a pretty big difference. I think it's still not quite ionic. It's like 1.9, so it's on that border. So it's very polar covalent. Um, the electrons are pulled closer to fluorine. So if you were to think about like the balance of the positive and negative charge, fluorine has more of the negative charge, just not enough that we would fully separate those and stick a negative charge on it like we would with an ionic bond. So we write these deltas. That's a lowercase delta, that squiggly thing. And so a delta means partial when you write it in lowercase. So delta positive, right? A delta with a plus sign is a partial positive charge. A delta with a minus sign is a partial negative charge. We also write this by drawing an arrow with a line through the end. And so what this arrow does is it points toward the more electronegative atom. And then the line is there to show you that this arrow means something specific, which is how the electrons are pulled. So the arrow part of the arrow is where the partial negative is. And then this end of the arrow, I've circled it. It kind of looks like a plus sign. That's where the partial positive end of that bond is. This is also, like when we write it this way, we'll call it a dipole moment. And a dipole moment, which we represent with the letter mu. So I don't think you'll see that used a ton in this class, but if you see a mu and it's talking about bonds, it's probably talking about the dipole moment. We use it to talk about also like how these electrons are distributed. What we will do in this class is a bit of an approximation based on electronegativity, but you can look up dipole moment values. It's measured in a unit called debye, and it takes into account the distance between the atoms and their electronegativities. But you will see the same kind of trend. So for a bond, a bigger difference in electronegativity means a bigger dipole moment.